Hello all. Let's start 7.8. 7.8 is improper integrals. Before starting with improper integrals, let's remind ourselves what we did up to now. Up to now, we learn how to deal with these types of integral. For example, if I have integral from a to b, f of x, a function, f of x dx, this function or this integral, we call it finite, right? Or definite integrals, correct? We call it definite integrals. It's finite. It starts from A to B. If I draw a graph for you, for example, this is X, this is Y, and my famous curve that I use always, right? This point is A, this point is B. Actually, integral means finding the area under the curve. It's finite. So start from somewhere, it ends somewhere else, right? I can say up to now, we were dealing with definite integrals or defined integrals. Our function is defined on a finite interval. This function is, you see, it's defined and it's finite interval. It starts from somewhere, ends somewhere, does not have an infinite discontinuity. Discontinuity. Your function is continuous. It doesn't have discontinuity. Discontinuity means it doesn't have a hole or it doesn't have irremovable discontinuity, which is a vertical asymptote. Hopefully these terms that I'm using, it doesn't have a hole or it doesn't have an asymptote or irremovable discontinuity. These terms that I'm using, hopefully your Calc 1 professor explained it well to you. Even the first day of the calculus class, which we explain a little bit functions, correct? And also in algebra, some professors, they are explaining what is a hole, what is removable discontinuity, what is irremovable discontinuity. These are the terms that I'm using. Hopefully, you know. Hole means if you have, for example, rational functions like this, x minus 1 over x squared minus 1, here your function as a whole, right? Because if you factor the denominator, you can cancel x minus 1 with x minus 1. For example, if you have a limit and x is approaching to 1, correct? Because if you plug in 1, here your denominator becomes 0, but you can factor, you can remove, it has a hole. But sometimes you end up with, you cannot remove that hole. That will be a vertical asymptote, or we call it infinite discontinuity, correct? In this section, we are dealing with integrals that they are infinite. In this section, we are evaluating. Let me write something for you. Evaluating integrals where interval is infinite, or has infinite discontinuity. Two types of them. I'll show it in a graph for you. What is infinite interval or what is infinite discontinuity? It means I will teach you this section in two different parts. Let's start with type 1. Type 1 is infinite interval. Let me draw a graph for you. Let me show it in a graph for you. Here, x, y, for example, I have this function y equal f of x. This is a function, some function f of x, correct? And this point is, let's name it a. And I'm sorry, somehow my internet disconnected. I don't know what happened. Let me start again from the beginning. Before, we were dealing with definite integrals. In definite integrals, our function is first defined, correct? And you are dealing with a finite interval. It starts from somewhere from A and ends somewhere in B. In this section, we are dealing with the functions that they have a discontinuity or they have infinite interval. We are dealing with integrals, right? We are looking for the integral. Integral means finding the area under the curve. For example, I put this graph for you. If you see this function f of x, my interval is infinite. It starts from A, but this side goes to infinity. The question is, can I find the area under this curve? It means, can I evaluate this integral? The answer is yes. This is your case 1 or type 1. Type 2, I will put both of them here for you, but I will explain one by one later. In type 2, let me graph something for you. For example, this is x, this is y, and I have something, a function maybe like this. Let me draw something. For example, something like that. Here I'll name B. Here I'll name it, for example, A. Type 2, you have a finite interval but you have discontinuity. You see here at this point, you have a vertical asymptote. Definitely, this is defined, but on one side, you have irremovable discontinuity. We are dealing in this section with these two types of integral. Let's start with type 1. I will not give you like your book at the beginning, definitely starting with a formula or a table. I will do an example for you, and in this example, I'll explain to you how to deal. Of course, the way that I will do example 1, it's not the proper notation, mathematical notation. Later, after I give you the rule, then you will see that how to start. I'll do more examples and you will see how to deal with these problems, but definitely not an example 1. Example 1, I'll try to explain how to deal with these integrals. For example, they are asking you to evaluate this integral. I have integral from 1 to infinity 1 over x squared dx. Correct? You see, starting from 1 to infinity. If you remember the graph of 1 over x squared, the graph of 1 over x squared is something like this. You have this side. And you have this side, which I'm not dealing with the left side because my integral starts from 1 to infinity. For example, if this is 1, from 1 to infinity, right? I want to find this area. This is type 1, correct? How to deal with these integrals? When I have here a notation of infinity, it's really difficult to deal with. I want to change this notation. To find that interval, I can do this. I can select a point, for example, here, and I will name this point, for example, T. If I put this point T, and later I'll move my T slowly, slowly, closer and closer, and closer, closer to infinity, then I can find this area, correct? For time being, I'm changing infinity to T. I will rewrite this problem as an integral of 1 to T 1 over x squared dx. Wow, right now I know how to deal with this integral. It's really, really easy how to deal with this integral, correct? Let's deal with this integral. Let's solve it. Instead of 1 over x squared, hopefully, because right now you learn a lot different types, different techniques of integrals. Do not make it complicated for you, correct? First, think what you can do. You see, if I move x squared in the top, it's really becoming an easy integral and I can deal with in a minute, correct? Then I will rewrite this one as an integral of 1 to t. Instead of 1 over x squared, I can rewrite this one as x to the power of -2 dx. Now it's easy to find this integral. What is the integral of x to the power of -2? You add 1 to the exponent, correct? If you add 1 to the exponent, that gives you x to the power of -1 over -1 from where? From 1 to t. And if you rewrite this one in a nice way, it gives you -1 over x from 1 to t. Now, plug in the upper limit, plug in the lower limit, or plug in the upper bound and lower bound, you can calculate easily this integral, which gives you -1 over t minus -1 over 1, which gives you -1 over t plus 1 over 1, which gives you 1. Now, this is not my answer. If you see the graph, I told you that I'll choose a point definitely greater than 1 on the right side of the 1, but I will move this point towards infinity. I will go closer and closer and closer to infinity. Remember calculus 1? When your professor starts and used this term, we are moving towards infinity, or we are going closer, closer to infinity. That gives you the idea of what? Limit. Oh, you're dealing again with the limit. Then to find the final answer, I will do this. I will take the limit of this answer. Limit as t approaching to where? To infinity of negative 1 over t plus 1. If you plug in t here, this part becomes 0. Correct? And your answer becomes what? 1. What was the goal? The integral was easy, or you will use a different technique of integral to simplify. Whenever you see one of these limits, the a or b in your integral, if one of them is infinity, you change your infinity to another variable. Usually in your book, they use t. You name it t, and you take the limit, correct? If I want to rewrite this problem from the beginning, definitely the way that I solve this problem, it's not the proper way or the proper mathematical notation that I used here. It's not the proper way. I will do this from the beginning. The problem was integral from 1 to infinity 1 over x squared dx. Okay, I'll change my infinity to t, but I will take the limit from the beginning, from step 1. I did it in the last step to just explain it to you, but after this, we do this. The limit t is approaching to infinity, integral from 1 to t 1 over x squared dx. I will change my notation, correct? Now, I'll give you some notes here, 2 easy notes. Type 1 has like 3, I can say 3 type or 3 cases. A, if you have an integral from a to infinity f of x dx, you can rewrite this one as a limit of integral from a to t, but your t should be approaching to where? To infinity f of x dx. Of course, here t should be greater than a number bigger than the lower limit, right? B, if you have integral, for example, from negative infinity to b f of x dx. In this case, name negative infinity t, right? Some professors, they use a and b, but in your book, the general form is in this way, and I really kind of agree with your book. This notation is the best notation. If you have from negative infinity to b, you can rewrite this one as a limit t approaching to negative infinity, integral from t to b f of x dx. In this case, your t should be less than what? Less than b, correct? Now, I will introduce a word or 2 words that maybe you are familiar with. Of course, a lot of you are familiar with those words. One of them is convergent. And the other word is divergent. What does it mean? What does it mean? Convergent. What does it mean? Divergent. Convergent means the area that we are adding gets smaller and smaller and smaller. Gets smaller. What does it mean? This is your graph. That was a graph that I did as an example for you. Here you have the area that we are adding, it gets smaller, 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 smaller. When your graph goes to infinity, you will add definitely a portion of it, which is really, 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 really close to zero, that you can ignore that portion, correct? Or in other words, I can say convergent means when your limit, when the limit exists, you can call it convergent. If the limit doesn't exist, we call it what? Divergent. In these problems, they're telling you, evaluate the integral and find out if it's convergent or divergent. After you take the limit at the last step, you see if your limit exists, of course, definitely it's convergent. If your limit doesn't exist, it means it's divergent. How to tell divergent based on the area? If your area gets bigger, 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 in this case, the area that you are adding, it gets bigger and bigger and bigger, we call it divergent. Or if the area gets bigger, like graph of cosine or sine, which is like this, right? We call these one divergent because it goes up, down, up, down, up, down. You cannot find these areas. That's why we call it what? Divergent, right? Now, using these two cases, I will do an example for you, correct? Or maybe two examples for you to show how to use. Example number one, evaluate integral from 1 to infinity 3 over x dx. Here you see my upper limit is infinity. Definitely, I will write my integral from 1. I'll name infinity. I'll change it to t, but outside I will put limit as t approaching to where? Infinity. 3 over x dx. Now it's easy to deal with this integral, right? Keep your limit. Please write your limit in every single step. Hopefully your calculus 1 professor told you that put the sign until you plug in the value of the limit, right? You have to write it in every single step, correct? Then my next step will be limit as t approaching to infinity. Here, instead of 3 over x, I can pull out the constant outside. I can write 3 integral from 1 to t 1 over x dx. Wow, very easy integral. I know already what is integral of 1 over x. It's ln absolute value of x. Even you can push this 3 before the limit based on the limit rules. Wherever you keep it, it's okay. Then you can write limit t approaching to infinity 3. What is integral of 1 over x? It's ln absolute value of x from where to where? From 1 to t. Before taking the limit, you have to plug in the upper and lower values here. Then your next step will be limit as t approaching to infinity, 3 times ln of, let me use bracket here, ln of, plug in the upper limit, absolute value of t minus ln absolute value of 1. Absolute value of 1 is 0, right? Sorry, the ln of 1, absolute value of 1, ln of 1 is 0, correct? Then I'll end up with limit t approaching to infinity 3 times ln absolute value of t. If you plug in here infinity, 3 times infinity gives you infinity. It means your answer is infinity. Now, is this integral is convergent or divergent? You see, your limit doesn't exist. It's infinity. Then definitely this problem is what? Divergent. Because your limit doesn't exist. Okay? Hopefully it will be clear for you how to deal with these examples or these improper integrals. Let's do another example. Example 2. Integral from negative infinity to 0 x e to the power of x dx. Here, my lower bound is negative infinity, then I will write limit as t approaching to negative infinity, integral from t to 0, x e to the power of x dx. This part is just new. How to deal with the integral of x e to the power of x dx. By looking to this integral, you should know which technique you want to use. I think in this part, you should use integral by parts, right? Algebra exponential. Then your u becomes x, du will be 1 dx or dx. Your dv is e to the x dx, then v will be the integral of e to the x dx is e to the x, right? Then apply the integral by parts rule here. You can write limit t approaching to negative infinity. Very bad notation. Let me erase it and read it. Limit t approaching to negative infinity, integral from t to 0 x e to the power of x dx equals limit t approaching to negative infinity, integral by part, u times v. How much is u? X, here a bracket, x times v e to the x from t to 0 minus integral from t to 0 v du. Your v is e to the x times du, which is dx. Hopefully you remember by parts. It was a few days ago, this lecture. If you don't remember, please open my video for integral by parts and review it. You see they're coming again and again and again as a part of a problem, correct? Okay, let's take this integral, then let's plug in the upper and lower limit together in both parts, right? Then you can rewrite limit t approaching to negative infinity, x e to the power of x from t to 0 minus, what is integral of e to the x? Integral of e to the x is e to the x. From where to where? From t to 0. Plug in the upper limit and lower limit in both parts, then this one equals limit t approaching to negative infinity. The first part, if I plug in, it will be 0 times e to the 0 minus t times e to the t minus this part, e to the 0 minus e to the t. This part becomes 0. Then you end up with limit t approaching to negative infinity, negative t e to the t. E to the 0 gives you 1, correct? Minus 1, and negative times negative gives you positive e to the t. Look, every time everything comes again and again to you. As a good student, when I see limit of negative t e to the t, if you plug in infinity here, it gives you infinity times e to the infinity gives you 0. Oh, you are dealing with limits that you have to use the technique of derivatives to find this limit, right? Minus 1 plus e to the t. Here I don't have problem. Here I don't have a problem. It's really easy limit. The only part here I have to deal with this limit, correct? Then I can rewrite that as a 3 separate limits. Limit of negative t e to the t as t approaching to negative infinity minus limit of 1 as t approaching to negative infinity plus limit of e to the t as t approaching to negative infinity. Using L'Hopital's rule here, because you saw I have infinity times 0. First, it's a product rule. I have to change it to quotient, right? Then this one I can write. If I put a small star here and 1, let's deal with this limit. The others are easy, right? Then I put a star. It means I'm just solving this part for you. You have limit negative t e to the t as t approaching to negative infinity. You can change this one as a t over e to the t, right? Limit of e, t over e to the t. You can keep the negative outside, correct? As t approaching to negative infinity. Now it's infinity over infinity, right? Then you can apply the L'Hopital's rule and you can rewrite negative limit as t approaching to negative infinity. The derivative of the top, which is 1, over the derivative of the denominator, which is e to the, sorry, here, negative t, which gives you negative e to the negative t, because I send it to the denominator, correct? And now, if you find this limit is actually what? 0. If I plug this part here and I find the other limits, it means if I go back here, I will have 0 minus, what is the limit of 1 when t approaching to negative infinity? Definitely 1. Plus, what is the limit of e to the t when t approaching to the negative infinity? This one gives you 0. Then my answer is what? Negative 1. You see, in one problem, I used integral by parts. In the second part of the problem, the L'Hopital's rule comes in, correct? It means that whatever you study in Calculus 2 in chapter 6, it comes back, it can come back in chapter 9 and chapter 10 as a part of the problem. That's why I'm giving you some time to go slower and learn all those techniques. Your eyes should be really familiar. As soon as you see limit negative t, e to the t, correct? Oh, this is L'Hopital's rule. Or if you see x, integral of x, e to the x, oh, I have to use here integral by part. That's why it's really important to have all those topics. Remember all those topics to can deal with these problems, correct? There are a lot of examples in your book. I just do less examples because it's a short-term course, but you can open your book and you can see a lot of examples. C, let's deal with another type of them. C, if you have integral from negative infinity to infinity, f of x dx, a function f of x dx, what should you do in this case? In this case, what you do, you can rewrite this one as an integral from negative infinity. You pick up a number between these two, I'll name it a, correct? F of x dx, plus integral starting from a to infinity f of x dx. In this case, f both integral from a to infinity f of x dx and integral from negative infinity to a f of x dx are convergent. It means their limit exists. Let's do an example, apply the rule. Integral from negative infinity to infinity 1 over 1 plus x squared dx. From negative infinity to infinity. I can rewrite this one as an integral from negative infinity. What is the best number between negative infinity to positive infinity? The easiest number to put here as an upper bound, or what should be a? If I choose 0, correct? From negative infinity to 0, from 0 to infinity. But I want to make sure if I plug in this upper limit here in the denominator, it doesn't change the denominator to 0. You see, if I plug in here 0, it doesn't change to 0, then 0 is the best number. Then I will rewrite my integral from negative infinity to 0, 1 over 1 plus x squared dx, plus integral from 0 to infinity, 1 over 1 plus x squared dx. Now you know when you have negative infinity, you can name it t and you can take the limit, right? Like part A and part B. I will rewrite this one, limit t approaching to negative infinity, integral from t to 0, 1 over 1 plus x squared dx, plus integral from 0 to t, 1. Oh, sorry, I have to put limit before that. I will put a space for my eraser. Plus limit integral from 0 to t, t approaching this time to infinity, 1 over 1 plus x squared dx. Correct? My recommendation in these types of problem is that you solve one of these first and see if one of them is convergent, the other one is also convergent. If one of them becomes divergent, the other one is also divergent. Don't do both of them together. My recommendation is put a star here, for example, star 1, and put a star here, star 2. First solve one of them, which one you like. And if you see if it's convergent, then solve the other one also. And at the end, add those integrals or add those areas, right? Let's start with the star 1. I have limit t approaching to negative infinity, integral from t to 0, 1 over 1 plus x squared dx. How to deal with this integral? What is integral of 1 over 1 plus x squared? If you remember, this one is, you can change it to trigonometric integral, correct? 1 over 1 plus x squared is inverse tan x, right? Then you can write this one as a limit tan inverse of what? X from t to 0. Plug in the upper limit and lower limit as t approaching to number 1 negative infinity. Then you can write limit t approaching to negative infinity tan inverse of 0 minus tan inverse of t. Tan inverse of 0 gives you 0, correct? Tan inverse of 0 gives you 0 minus tan inverse of t. Let me write. Still you have your limit, t approaching to negative infinity, tan inverse of t. If I plug in infinity, if you remember the graph of tangent, when the graph of tangent goes to negative infinity, definitely that's pi over 2 or negative pi over 2. That means you will end up with 0 minus negative pi over 2, right? Which gives you pi over 2. Is this convergent or divergent? Definitely, this is convergent. If you do solve the second part, which is totally the same, you will get another pi over 2. Then what is your final answer? Your final answer from negative infinity to positive infinity, 1 over 1 plus x squared dx actually equals pi over 2 plus pi over 2, which is the second portion. I didn't solve it. Please find the second star limit also, which is totally the same. I'm saving time. If you solve that one, you will get another pi over 2. What is pi over 2 plus pi over 2? It gives you 2 pi over 2, and you can cancel the 2, which gives you what? Pi. It means the area under this curve from negative infinity to positive infinity is what? Pi. Correct? This was all about type 1 of this continuity. I will stop the lecture here because the second type of this continuous integrals, they are really a little bit longer lecture. I will put another part of the video during the week for you. And I'll stop the lecture. Please practice with these problems. They are not difficult if you remember your calculus 1 and also chapter 6 and chapter 7 from 7.1 to 7.4. See you next time for the second part of 7.8.